Hello, everybody. Welcome to section 10.3 on polar coordinates. So this is our last section together of new content. And like parametric equations, kind of like thinking about describing curves, points, in a radically different way. Not that radical, but rather different than what we've been doing traditionally the whole way through. The really good news, though, is we don't have to reinvent calculus. All of our stuff just kind of applies here. And so my main goal here is to kind of introduce these polar coordinate system to you. We're going to look at some curves. We're going to do a little bit of differentiation and try to convince you that, ta-da, we don't need to go start from scratch. Okay, we've developed all of this theory. We get to use it here too. And that's a really powerful, wonderful thing. Okay? So, what am I talking about? Here's our motivation. Given a point in the plane, how do we describe its position? So traditionally, you would have said, well, this has coordinates x, y, with x being the horizontal distance away from the vertical axis, which is y. All right, going to label our x-axis. And then y is our vertical distance away from the coordinate axis, okay? Our horizontal axis is fixed, our vertical axis is fixed, and that is kind of this. That's kind of it. You hopefully have a lot of comfort with this at this point in your math journey. Okay, so this is called the Cartesian system. We've talked about this before, the Cartesian coordinate system. We're fixing our axes in place. Okay, and then we are looking at any point, and we're going to describe the position of that point away from our x and y axes, okay? And this is as a unique descriptor, okay? So, given any point in space, we don't have to stay in 2D, but we can extend to 3D. We haven't done that here. There is absolutely, this can be extended. We can describe its position uniquely relative to the x and y axes. Okay, so you should be pretty comfortable with that. I hope so. All right. Now, polar coordinates takes a slightly different approach, and what we do is we fix the pole. We call it the origin. Okay. Nope, not. We spell pole correctly. Okay. This is fixed. Okay, and we call this the polar axis. Okay, and it is fixed. And those are our fixed things that we're going to position our point relative to. How do we do that? Well, there is some distance this point is away from our pole. We're going to call that r. And the line, the ray that is made between the pole and our point with the polar axis, it makes an angle. And that is our polar coordinate of this point. This is our polar coordinate system. So unlike in the Cartesian system, this is the property that you actually could have more than one way of defining a point. Okay, so while over here, gray is an unusual choice, we have this unique description of its position, or unique description. Here, this theta can actually, we can add 2 pi on. All right, so that is something that we're going to have to watch out for. It makes things, just adds a little layer to them for us. Unlike the Cartesian system, it has the property that points can be defined by different polar representations, or coordinates, let's say representations. Okay, so let's see this in action. Let's first define things a little bit more clearly. So we have our point, call it the plane, choose a point in the plane, call it O. This is our pole, okay, O. We're choosing a ray starting at O, calling it polar axis. So this is our polar axis. Sure, there's our polar axis, okay. Take any point P except O in the plane. Okay, so this is my point P. Right, that's what I'm measuring. Measure that distance, call that distance R. Okay, that's what we talked about there. So that is this distance R. Okay. Then you're measuring the angle between the polar axis and the ray. All right, so let's do angle between the polar axis and the ray. All right, so this angle here, that's our theta. Okay. Theta measures this in radians. And there's this thing about a bijection, but that R and theta are called our polar coordinates. Okay. So let's actually see this in action. I do want to do this on this particular set of videos. So how do we do this? Well, we are looking for A here, asks us to find a point that is of length 1 and angle pi over 4 with the pole. Okay, so here is our pole right here. This is our polar axis. All right, pi over 4. It's like this. This line makes pi over 4 with our here, like pi over 4, right? And then really just plop a point, down on that line. Declare that 1. And then we would label this point with 1 pi over 4. Okay. All right. Part B here, we're looking for 5 pi over 4. So I don't know, what do we do? 5 pi over 4. Well, that is 4 pi over 4 plus pi over 4. So that is pi plus pi over 4. So we've gone all the way there. That's pi. And then we go around to here and we get our ray. And plop a point down on that ray, and we call that distance 2. And so this is 5 pi over 4. Okay. 2 negative pi over 3. So we are absolutely using the convention that positive angles go counterclockwise as always. Okay. And negative angles go clockwise. Okay, this is not different from anything you've seen before when we're talking about angles in our unit circle. So, negative pi over 3, well, declare that pi over 3, plop a point down there. Nope, not 2, not 3, it's 2. 2 negative pi over 3. All right, that is our point. And maybe call that 2 to make it clear. D. So let's just go A, B, C, D. Negative 1, 5 pi over 6. Okay, so let's first handle the 5 pi over 6. So that is a little less than pi, and so we're somewhere over here. We're calling this 5 pi over 6. But what about the negative? Well, we need a convention, okay? We need a convention, and basically what's going to happen is we're going to throw it to the other side of this exact same line. We're just going to extend our line through the pole down to that fourth quadrant, all right? And look one distance away over here, okay? So this is distance 1, but it has coordinates -1, 5 pi over 6, all right? So if this was our point here, this would have 1, 5 pi over 6. Okay, we need to flip it back across the pole. Okay, so let me be very clear about that. Convention. Negative R values we position them on the opposite side of the pole. Okay, and I kind of really want to so this is the opposite side. That's what's happening here. Okay, so let's, with that in mind, we're going to plot a couple more points. Okay, so let's do 1 pi over 2. So pi over 2 is here. So this is, and then, I don't know, call this 1. So this is the point 1, pi over 2. Okay, great. 5 pi over 2. Okay, so 5 pi over 2 is equal to 4 pi over 2 plus pi over 2, which is equal to 2 pi plus pi over 2. So I go all the way around once, and then I go this way. Okay, so this 2 pi is this part, and this pi over 2 is this part. Okay, and then again, I position myself up 1, and I call this 1, 5 pi over 2. All right? Trying to drive home a point here. Haha, I don't mean to make puns. So now we're going 3 pi over 2. 3 pi over 2. Well, that is 2 pi over 2 plus pi over 2. So that is pi plus pi over 2. Or maybe you just know this really good. So there's pi. And here's pi over 2. So here's pi. And here's pi over 2, going a little bit further. But our negative means we are slingshotting, flipping back over, and we're getting the point -1, 3 pi over 2. Okay, so down here is 1, 3 pi over 2. Okay, so the point that I made above here stands. Points can be defined by different polar representations. I have given 3 different polar representations, polar coordinates, for the exact same point.